statistical goodness of fit, that's this part, number of parameters, this part. And we're going to use this one rather than the R squared one, because this one is typically better in the sense of the following idea. Have you ever heard of cross-validation? Here we are doing forecasting. If you think about R squared, what is R squared doing? R squared is the goodness of it. Basically, R squared, let me go to the end where I have an empty page. So R squared is like this. How good is our regression line in capturing our observations? How well does this line reflect all these points? But now think about forecasting. Is this really a good measure of what we need for forecasting? This line tells us how good are we predicting the things we already know. Yeah? The sample we know already. We know the sample. But what is forecasting? It's basically predicting something you don't know. You want to predict the next point that you don't know yet. So this line might be very good at predicting this point, but very bad at predicting that point. So what we really would like is a measure of fit for out of sample forecasts. How good are we at out of sample forecasts? This is in sample prediction. So cross-validation is basically that idea. Cross-validation is basically going to say, let's not use all observations. Let's take this, let's exclude this observation, and then see how good we are at predicting this observation. So that's kind of cross-validation. Leave one out and predict the one you left out. Then you look at how good am I at predicting this point that I left out. How good am I predicting out of sample rather than predicting in the sample. And so the Schwartz criterion basically in big samples converges to this out of sample forecast measure. So rather than having an in sample R squared, you can have an out of sample R squared. How good am I in terms of forecasting things I don't know, rather than predicting things I already know? And forecasting is that, predicting things you don't know, rather than predicting things you already know. So the Schwartz criterion is better than the R squared in terms of this out of sample forecast. That's the crucial thing. So we're going to lower better because it's out of sample forecasts. We do out of sample forecasts. So let's now look at our result. Schwartz criterion. Here we say it's 23.1. If we look at trend XB, $23.3. So we use the linear trend. So that's why we have this table. This is a table you should have in your report. This is a table you always will have to fill in. You compare the Schwarz criterion for trend XB and trend lin and choose the lowest one. So you run your regressions, fill out this table, boom, result number 1. You know what is giving the better fit if I have a linear model or a logarithmic model. We can also look at the residuals and see whether we see a difference there. View actual fit of residual graph. In this case, if we look at the residuals, this is the residuals for the XPB file. If you look at the residuals for the other one, trend lin, if you look at actual fitted residual graph, we'll see fairly similar residuals. So here, the difference between the two is not huge. Right? But if we are strict about the Schwarz criterion, we're going to say the one with the lowest Schwarz criterion is the one we want. Okay.
Can you show how you know that you
Yes. View. So you go to estimation output. Once you have an estimation output, I don't know why. Then you just say view actual fitted residual, and then the graph. So once you have your estimation output, you can see different views. All the representations is just okay. Representations gives you. I don't know why it isn't. This is one kind of representation. The comment you gave, the estimation equation, then with the coefficient, you can see it in this way, or you can see it in very graph ways. All different ways to see the same thing. So summarizing, step 1 is once we put our series into Excel, gave it the data name, run program 1, compare the Schwarz criterion of the two models that are actually comparable, the linear model and the non-linearly squares model, choose the lowest. Schwarz criterion, that's your decision in terms of trend. Okay. No questions? Easy to do now. Okay, now let's go to the second program. You see here, we have our peaks, seasonality. So now let's see how we can capture seasonality. So download from Learn Step 2 program, and you will see it looks a bit like this. So here we assume that our first program suggested we should take logarithms. And we assume we have monthly data. Because that was our conclusion, and because this is the kind of data, we're going to have log data everywhere. Suppose we found, based on step 1, that we didn't have a logarithmic trend, but a linear trend. Well, then you will have to modify the program. You will have to delete logarithm here, logarithm here, logarithm here, logarithm here. So this is why forecasting becomes a bit more complicated. We have our basic programs, but these basic programs are valid for a given scenario. But your scenario can be different from the scenario that we cover here in class. So you will have to decide which scenario am I in, and how do I make modifications to my program. Like here, if it's logarithm, if you find your series have a logarithm trend, use it. If it's a linear trend, modify it by deleting logarithms. Similar, we have monthly data. So we have 11 seasonal dummies. Well, what do you have to do if you have quarterly data?
3 dummies.
3 dummies. Quarter 1, quarter 2, quarter 3. Quarter 4 becomes the benchmark. Well, tell me, what is this program about? What do we do here? Well, we have 1 equation, 2 equations, 3 equations, 4 equations. Let's compare the different models. Model 1, a regression on just a constant. Model 2, a constant and seasonal dummies. Model 3, a constant and a trend. Model 4, a constant, trend, and seasonal dummies. Four different models. We're going to estimate models with no trend and no seasonality. Here. If you find this one is the best, no trend, no seasonality. Here we say, okay, we don't need a trend. We thought we have a logarithmic trend, but in fact, after looking at it more carefully, maybe we don't really need that trend. Here we say, okay, maybe we need a trend, but we don't need seasonal dummies. Here we say, oh, maybe we need everything. Okay. So run the program and tell me what you decide. So you get program 2. So usual thing, we copy and paste our program, run it, and then look at the outputs. And you have the work file. You will see now trend sees 1, sees 2, sees 3, sees 4. Trend sees was already there from the previous program. But now we focus on Cs1, Cs2, Cs3, Cs4. How are we going to compare the models? Same thing as always, Schwarz criterion. So now look at the 4 outputs and see which one has the lowest Schwarz criterion. Basically, a new table. We make a new table that summarizes the 4 possibilities. No trend, no seasonality, just a constant. No trend, yes seasonality, a constant and seasonality. Yes trend, just a trend, no seasonality. So you have the constant and the trend. Or we have everything. So write down the table, the name of the equations, well, fill in the Schwarz criterion. So trend season 1. Trend season 1. Schwarz criterion 0.49. That's just a constant. Trend season 2. 0.64. Trend season 3. Minus 1.95. Okay, that's already better. Last one. Minus 254. Schwarz criterion minus 2.4. This one is the best one.
Is there ever a time where the constant would be this small? Or is that never true?
It depends on your series, no? So if we think about it, what kind of a series would have a constant only? If you have a constant only, we would have something like this. No? We have a constant series. And we maybe have just a little bit deviation around it, without any kind of, just a random noise around it. That would be a constant.
Okay.
That's possible.
Also,
I think in
it's
mo-
like a trend of 0.
Trend of 0, okay, there's no trend. There is no seasonality. There is no cycle. Well, cycle we didn't check it, but here there's no seasonality and no trend. So it's possible. So okay, here we find this is minus 2.54. This is the lowest one. So what is the implication of this? The implication of this, from now on, from at the end of step 2, we're going to use this model. Whenever we think about cyclicality, because now we have done trend, and we have done seasonality, and we saw we need both. When we now go look at cyclical things, we will start from this model. We're not going to look for cyclicality here. We're going to use this model before we go to cyclicality. Because this is the best model when we compare these 3 models. From now on, in any model that we will estimate, we'll include not only a constant term, but also a trend and seasonal dummies. So now we go to cyclicality. We know everything in terms of the trend. We know everything in terms of the seasonal dummies. Now let's go for cyclicality. So if we look at this at our most preferred model, the most preferred model has both trend and seasonality. Now let's look at the residuals. So let's take our graph, actual fitted residual graph. So trend is easy to see. It just goes up the whole time. That's trend. It always moves in one direction. Seasonality, easy to see by the eye. You get these peaks at a specific months are different. You see a specific pattern across the month. Now, if we look at our residuals after we take out the trend and after we take out our seasonal component, what do you see? If you look at this residual,
Positive autocorrelation.
indeed, you see autocorrelation. You have low residual is followed by another low residual. A big residual is followed by another big residual. Low residuals again followed by other residuals. It's not, we clearly don't have a random thing here, no? It is clearly serial correlation. Right? If we would get kind of just a cloud of points here where there was no clear pattern, we could say, okay, probably there's no cyclicality. But here, when we kind of clearly see this autocorrelation, that suggests there is some cyclicality. So see what we do here. While we do all our econometric tests, visual inspection already shows us a lot of things too. Visual inspection shows already whether there's a trend or not. Visual inspection already suggests whether there's some seasonality or not. Visual inspection already can give us a hint about can we expect cyclicality or not. So let's now discuss a little bit about this moving average. And autoregressive terms. This would be an autoregressive process. Autoregressive 1. We have one lag of our dependent variable. Well, this would be alpha plus beta y minus 1 plus gamma y t minus 2 plus eta 2. Could be autoregressive of the order 2. No, we have two lags. Three lags, autoregressive of the order 3. 4 lags, autoregressive to the order 4. You see the pattern. Now forget about this one for a moment. And let's focus on this first one. If this is true, then y t minus 1 is what? It's alpha plus beta y t minus 2 plus eta t minus 1, right? 1, 2. If t is a function of t minus 1, well then t minus 1 is a function of t minus 2. And here we have the error term t, so it's the error term t minus 1 here. Now substitute this one here. You get, okay, y t is so is alpha plus beta times y I t minus 2 plus eta t minus 1 plus eta t. Or this is alpha plus beta times alpha plus beta square y t minus 2 plus eta t minus 1 plus eta t minus 2, eta t, and here we have beta. So if we substitute it, forget about this part, what we get here, we have beta to the power 2, t minus 2. But then we have here eta t as before, and also eta t minus 1. So if you would substitute and substitute this, you would get something like yt is something something something, b to the power n yt minus n, plus eta t plus something eta t minus 1 plus something eta t minus 2 plus eta t minus n. Right? So if you would continue to substitute it, you would get something that yt is basically a function of a series of shocks. And here we have beta to the power n. Beta to the power n will, this is basically a number between 0 and 1, so basically it disappears. So that's kind of the Wall theorem, which says that any series can be basically expressed as a series of shocks. And these terms here, all these etas, these are the MA terms. These are basically lags of the shocks. These are all the MA, the moving average. It's basically kind of a lag of a shock. So we started with 1 here. Y is a function of yt minus 1. But alternatively, we can write it as this. Yt is a function of all these shocks. Clear or not clear? Not clear. Okay.
Yeah, I know the
This is your substitute. Now continue to substitute. Because here we have yt minus 1. We can also say yt minus 2 is what? Well, yt minus 2 is, if you say 3, yt minus 2 is alpha plus beta yt minus 3 plus beta t minus 2. So here we substitute 2 into 1. We get yt is a function of yt minus 2. Yt minus 2, well, substitute it here. And continue to substitute and substitute and substitute. What will we end up with? We will end up with a formula like this. Yt is a function of lots of eta t's, all lagged at the various degree. No?
But how? Okay, yeah.
So you get here kind of, if we go from yt, here we have eta t, then we get rid of yt minus 1, well we have eta t still, but we also have eta t minus 1. Substitute again, you get also eta t minus 2 there. Substitute again, you get eta t minus 3 there, and so on. So okay, we have an AR representation. We can also do it as an MA representation. Right?
Did you say there's a coefficient on those error terms?
Yes, there are coefficients on these error terms too. Yes. I don't know exactly, you can work it out and you will see it. Like here it would be beta eta t minus 1. Then you will get probably beta to the power 2, or probably beta to the power 2 and beta to the power 3 and so on. So you will get all kind of coefficients. All kind of coefficients that you can estimate too. Huh? So,
what does this mean? Like why we should get the last one?
So now what we can do is we can say, okay, we can estimate this equation, or we can estimate this equation. Here we would estimate all these coefficients of all these etas, or we can estimate this equation. Of course, this was a fairly simple one, but suppose that this is a true one. Then you get a whole mix of things, a very complicated one. In practice, we don't know whether our model is like this or like this. So we don't know which of these models we want to estimate. We might want to estimate, well, just something like this, or we want to have a combination. We can say, okay, we can estimate many different models. Let me see whether we have them on here. Okay. So we don't know which one is correct. Let's experiment. Here, for example, the first thing that we will do is, let's try this one. Since the Wall theorem says every series can be expressed as a sum of many error terms, as a sum of many moving average terms, let's do this one. Let's say we're going to run a regression with a trend and seasonal dummies, because that's what we found. We found we have to include a trend and seasonal dummy. Let's now include 20 MA terms. This is eta t minus 1, eta t minus 2, eta t minus 3, eta t minus 20. So basically you say here, y is a constant plus beta times trend plus the sum of all the seasonal dummies, so gamma times I seasonal dummies, I, plus, well, we always have eta t with a quotient of 1. That's standard. But we can also have plus, say, omega 1 eta t minus 1, plus omega 2 eta t minus 2, plus and so on, plus omega 20 eta t minus 20. Since every series can be expressed as a sum of this kind of things, let's just include 20. You like this one or not?
No.
Why not?
It's too complicated. It's like too much terms.
Too many terms. Because that's indeed, that makes sense, kind of estimating many parameters. Why don't you like to estimate many parameters? Because okay, why do we stop at 20? Why don't we put 100 there? Or maybe even 500, because we don't know the real number, no? We could say, okay, well, adding 20 is already a lot, because the more variables or the more coefficients we estimate, the more imprecise results we get. High standard deviation, kind of made also big forecast errors. So we don't like to estimate many parameters as a starting point. But, I mean, as a first step, why not try? So, well, before we do that, let's take another 5 minutes break.